Hello there, and welcome to our journey through the most alarming discovery in modern astronomy. Tonight we will explore something extraordinary, something ancient, and something that is hurtling directly toward us from the vast darkness between the stars. We are going to discover the terrifying trajectory of an interstellar visitor that has traveled billions of years to reach our cosmic neighborhood and may not be planning to simply pass by. Not just another asteroid or comet from our solar system, but a true wanderer from the depths of space, carrying secrets from stellar nurseries that existed long before our Earth was born, and possibly carrying a death sentence for our planet. We will explore the ominous trajectory that brings this ancient traveler on what appears to be a collision course with our solar system, and what its approach might mean for the survival of everything we know. Before we begin this exploration, I would love to know where you are listening from tonight. Perhaps you are in a quiet room, maybe lying back with your eyes closed, unaware of the cosmic threat racing toward us through the darkness. No matter where you are, we share this moment together, floating on our small planet through the vastness of space, potentially in the path of an unstoppable force from beyond the stars. If you find these kinds of urgent astronomical revelations compelling, I would be grateful if you could subscribe or like this program. It helps this critical signal reach other minds who need to understand the cosmic dangers that may be approaching our world. Take a moment now to settle in. Let your thoughts expand to grasp the terrifying scales of destruction that may be heading our way. Could a Harvard professor be correct about an alien spacecraft disguised as a comet? The question sounds like something from a science fiction thriller, but on a warm July morning in 2025, this precise debate began rippling through academic circles worldwide. The catalyst was an object designated 3I Atlas, racing through our solar system at unprecedented speed, and the controversial claims of one of America's most prominent astrophysicists, Abraham Loeb, known simply as AV to colleagues, occupies an unusual position in modern astronomy. The Frank B. Baird, Junior Professor of Science at Harvard University, carries impressive credentials. His research spans 8 published books, nearly 800 academic papers, and decades of contributions to theoretical astrophysics. Yet by July 2025, Loeb had become equally famous for something else entirely: his willingness to publicly consider possibilities that make other scientists deeply uncomfortable. When Atlas telescopes in Chile first detected the interstellar visitor on July 1st, 2025, most astronomers saw exactly what they expected: a frozen relic from deep space, following natural physics as it approached our sun. The object appeared roughly 3.5 miles wide based on initial observations, traveling at 209,000 kilometers per hour. These measurements alone marked it as extraordinary, representing the fastest recorded velocity for any visitor to our solar system. Within days of the discovery, however, Loeb began asking different questions. Rather than accepting the obvious classification, he started examining what he called anomalous characteristics. The orbital plane of 3I Atlas lay within 5 degrees of Earth's own orbital plane around the Sun. For an object originating from interstellar space, this alignment struck him as remarkably precise. Statistical analysis suggested such positioning occurred with probability less than 0.2% for random interstellar objects. The Harvard professor noted additional curiosities as observation data accumulated. Unlike typical comets, 3i showed no clear evidence of the gaseous tail that defines cometary behavior. Spectroscopic analysis revealed none of the expected molecular signatures astronomers associate with sublimating ice and dust. The object's trajectory would carry it unusually close to Venus, Mars, and Jupiter during its solar system passage. Loeb calculated the probability of such planetary encounters at approximately 0.005% for randomly arriving interstellar bodies. By July 15th, these observations had crystallized into formal academic speculation. Loeb collaborated with researchers Adam Hibbard and Adam Kroll to produce a paper titled "Is the Interstellar Object 3I Atlas Alien Technology?" The document, uploaded to the Arxiv preprint server, presented what the authors described as largely a pedagogical exercise. They emphasized the paper was fun to explore, irrespective of its likely validity. Nevertheless, the implications they outlined proved anything but playful, drawing upon the dark forest hypothesis as a resolution to the Fermi paradox. The researchers suggested 3 Atlas could represent hostile extraterrestrial intelligence. The dark forest theory proposes that advanced civilizations remain hidden because revealing their existence invites preemptive destruction by other species competing for finite cosmic resources. Under this framework, any interstellar visitor might arrive with malevolent intent. The paper detailed how 3I Atlas would achieve perihelion on the opposite side of the Sun relative to Earth. This positioning could be intentional to avoid detailed observations from ground-based telescopes when the object appeared brightest. The authors noted this hidden vantage point would provide optimal conditions for a reverse solar oberth maneuver, an advanced propulsion technique that could allow the object to brake and remain bound to our solar system. Such technical speculation represented typical Loeb methodology. Rather than dismissing unusual observations, he constructs alternative explanations that challenge conventional assumptions. His approach stems from decades studying the first stars, black hole formation, and the future evolution of the universe. This research background gives him familiarity with extreme cosmic phenomena that most astronomers never encounter professionally. The Galileo Project, which Loeb launched in 2021, reflects his commitment to systematic investigation of unexplained phenomena. The International Research Initiative searches for extraterrestrial intelligence and technology on and near Earth. Its founding followed the release of government UFO reports and NASA Administrator Bill Nelson's call for scientific analysis of unidentified aerial phenomena. When Loeb emailed NASA suggesting such research but received no reply, he organized private funding to pursue the work independently. This institutional independence shapes Loeb's willingness to advance controversial hypotheses. Unlike researchers dependent on government grants or traditional academic hierarchies, he operates with donor support specifically intended to explore unconventional possibilities. The financial backing comes from individuals who explicitly want investigation of potential extraterrestrial contact, creating incentives for bold theoretical speculation. Academic colleagues view this arrangement with mixed feelings. Some appreciate Loeb's courage in addressing topics that conventional peer review processes might reject. Others worry that publicity-driven research undermines the careful methodologies that distinguish science from speculation. The tension became particularly acute with 3 Iatelis, As Loeb's media interviews and blog posts reached public audiences before traditional peer review could evaluate his claims. Speaking to CBS Boston in late July, Loeb outlined his reasoning with characteristic directness. We should put all possibilities on the table that it is a rock, a comet, or something else until we get the evidence, he explained. The data will tell us what it is. His approach reflects genuine uncertainty about the object's nature, combined with skepticism about premature scientific consensus. The professor emphasized the stakes involved in such determination. I think that when we have a blind date from a visitor from another star, all bets are off, he told reporters. We should not assume anything, and we should assess the risk given the data that we have. This risk assessment framework treats potential alien contact as analogous to natural disaster preparedness, requiring systematic evaluation regardless of perceived probability. Loeb proposed developing something like the Richter scale for earthquakes to measure potential extraterrestrial threats. 0 would represent a natural object like a comet, while 10 would indicate definite technological signatures requiring policy responses. Such classification systems reflect his conviction that extraordinary claims demand extraordinary preparation, not just extraordinary evidence. The Harvard astronomers' public statements generated immediate controversy within professional astronomy communities. Critics argued that speculating about alien technology without compelling evidence risked damaging public trust in scientific institutions. They pointed to previous instances where preliminary observations of unusual objects eventually yielded conventional explanations through continued study. Yet Loeb maintained that dismissing possibilities prematurely violated scientific principles. In subsequent blog posts, he compared contemporary skepticism to historical resistance against Galileo's telescopic observations. He argued that maintaining childhood curiosity about cosmic mysteries was more valuable than pretending to know answers in advance. This philosophical stance places him at odds with colleagues who prioritize caution and methodological conservatism. The academic tension intensified as media coverage amplified Loeb's speculations. Headlines proclaimed possible alien spacecraft approaching Earth, often omitting the conditional language and uncertainty markers that scientists use to qualify preliminary hypotheses. Social media transformed nuanced theoretical discussions into sensational claims about imminent extraterrestrial contact or potential invasion. Professional astronomers found themselves responding to public questions about alien threats based on unconfirmed interpretations of limited observational data. The situation illustrated ongoing challenges in science communication, where academic hypotheses intended for expert evaluation become public narratives with dramatically different implications and emotional impacts. Loeb acknowledged these concerns, but defended his communication strategy. Rather than restricting discussion to closed academic circles, he argued for transparent public engagement with cosmic mysteries. If we are probably not alone in the universe, as he often states, then citizens deserve participation in debates about potential contact scenarios and appropriate responses. The controversy surrounding 3 IATLs thus reflects deeper questions about how science should operate in an age of instant global communication. Traditional academic processes assume months or years for hypothesis development, peer review, and consensus formation. Modern media cycles demand immediate expert commentary on breaking developments, creating tension between careful methodology and public information needs. By August 2025, Loeb had published multiple blog posts analyzing new observational data from 3I Atlas. Each analysis maintained his characteristic approach, acknowledging conventional explanations while systematically exploring alternative possibilities. He examined brightness variations, trajectory refinements, and spectroscopic measurements as potential evidence for either natural or technological origins. The Harvard professor's persistence reflected his broader intellectual project of expanding scientific consideration of extraterrestrial phenomena. Through books like Extraterrestrial and hundreds of academic papers, he has consistently argued that the universe likely contains numerous technological civilizations. Finding evidence for such civilizations, he believes, could represent the greatest discovery in human history. This conviction drives his willingness to endure professional criticism and public ridicule. Loeb often notes that scientific progress requires individuals willing to challenge prevailing assumptions, even at personal cost. His 3 Atlas hypothesis exemplifies this philosophy, advancing uncomfortable possibilities that most colleagues prefer to ignore. As September 2025 approached, the academic debate over 3 Atlas continued evolving. New observations would either support Loeb's speculations or reinforce conventional Comet interpretation. Either outcome would have significant implications for how the scientific community approaches future interstellar visitors and the eternal question of whether we are alone in the cosmos. The Harvard challenge posed by Avi Loeb thus transcends simple questions about one unusual object that reflects fundamental tensions between scientific caution and intellectual boldness, between institutional consensus and individual investigation, between professional peer review and public engagement. These tensions will likely persist as long as humans search the cosmos for signs of intelligence beyond our own world. At NASA headquarters in Washington, D.C., on a humid September morning in 2025, Dr. Thomas Statler prepared for another day of managing scientific controversies that most people never imagine. His office walls displayed images from successful planetary missions, DART's impact with asteroid Dimorphos, Lucy's journey to the Trojan asteroids, and artistic renditions of future explorations. These achievements represented years of careful institutional science, methodical peer review, and measured public communication. Now, however, Statler faced questions about potential alien spacecraft that demanded equally careful responses. As lead scientist for Solar System Small Bodies in NASA's Planetary Science Division, Statler oversees research programs investigating asteroids, comets, and other debris throughout our cosmic neighborhood. His responsibilities span multiple concurrent missions worth hundreds of millions of dollars, involving thousands of scientists across dozens of countries. The work requires balancing scientific curiosity with institutional credibility, public excitement with professional caution, and extraordinary claims with extraordinary evidence requirements. The path that brought Statler to this position began decades earlier at Princeton University, where he earned his PhD in astrophysics in 1986. His doctoral research explored fundamental questions about galactic structure and cosmic evolution, topics that seem abstract until they inform practical decisions about planetary defense and mission planning. After nearly 20 years on the faculty at Ohio University, where he founded the Astrophysical Institute. Statler joined NASA in 2014 to help translate academic research into operational space science. His academic background provides essential perspective on the 3I Atlas controversy. Unlike researchers focused on single specialties, Statler understands how different astronomical phenomena connect across scales from individual objects to entire galactic systems. This broad view helps him evaluate extraordinary claims within appropriate scientific contexts, recognizing which observations represent genuine mysteries versus expected variations in natural processes. When Harvard's Avi Loeb began suggesting that 3I Atlas might represent alien technology, Statler found himself in a familiar institutional position. NASA scientists regularly encounter claims linking unusual observations to extraterrestrial intelligence, from radio signal anomalies to unexplained atmospheric phenomena. The agency has developed careful protocols for addressing such speculation while maintaining both scientific integrity and public trust in institutional expertise. Speaking to reporters from The Guardian in September 2025, Statler delivered NASA's measured response to the alien hypothesis. "It looks like a comet," he stated with characteristic directness. "It does comet things. It very strongly resembles, in just about every way, the comets that we know." This assessment reflects months of detailed observation by multiple telescopes and research teams, all pointing toward conventional explanation rather than technological origin. The NASA scientist acknowledged that 3 Atlas possesses some interesting properties that are a little bit different from our solar system comets. Such differences might initially seem significant to outside observers, but Statler emphasized that comets regularly display unexpected behaviors as they respond to solar heating. Even objects from within our own solar system can have a history of suddenly brightening if there is, say, a particular pocket of ice that sublimates quickly and drives off a large amount of dust. This explanation illustrates Statler's institutional approach to unusual observations. Rather than dismissing anomalies outright, NASA scientists investigate systematically while maintaining appropriate skepticism about extraordinary interpretations. The process involves comparing new data against established understanding of natural processes, looking for patterns that might indicate either conventional mechanisms or genuinely unprecedented phenomena requiring revised theories. Statler's career experiences inform his confidence in conventional explanations for 3 Atlas through programs like DART, which successfully redirected an asteroid's orbit in 2022. He has worked extensively with unpredictable small body behaviors. Asteroids and comets regularly surprise researchers with sudden brightness changes, unexpected rotational states, and irregular material composition. Such variability represents normal characteristics of objects subjected to complex physical forces over millions of years. The lead scientist explained to media outlets that comets are mixtures of dust and ice. They are being heated by the sun, that heating is changing, and exactly how they respond to that is something that is a bit unpredictable. This statement reflects deep understanding of cometary physics, developed through decades of observations and theoretical modeling. What appears mysterious to casual observers often fits established patterns recognized by specialists familiar with the underlying physical processes. Institutional scientific communication requires careful balance between honest acknowledgement of uncertainty and premature speculation about extraordinary possibilities. When Statler states that evidence is overwhelmingly pointing to this object being a natural body, he uses language that conveys confidence while avoiding absolute certainty, claims that could prove embarrassing if future observations reveal unexpected characteristics. Such measured phrasing reflects professional training in hypothesis evaluation and public science communication. NASA's approach to the 3I@L's controversy also demonstrates institutional memory from previous interstellar visitor episodes. When Oumuamua passed through our solar system in 2017, similar speculation arose about potential artificial origins. Careful analysis eventually revealed natural explanations for most anomalous characteristics, though some questions remain open for continued research. This experience provides context for evaluating claims about 3I@L's without dismissing legitimate scientific inquiry. Statler emphasized that interstellar visitors like 3I Atlas are special because we now have the ability to discover these interstellar comets. It is not that they are really anything new, but we have just recently had the ability to discover them, and we have discovered only 3 so far. This historical perspective helps contextualize current observations within the broader evolution of astronomical detection capabilities and theoretical understanding. The NASA scientist views 3I as providing a window we have never had before, directly into the composition of other solar systems. This scientific opportunity represents the primary institutional interest in studying the object, focusing on what chemical and physical information it might reveal about planetary formation processes in distant stellar environments. Such research questions offer concrete investigative pathways, regardless of whether the object displays conventional or anomalous characteristics. Behind Statler's public statements lies complex institutional machinery for evaluating extraordinary claims. NASA maintains formal protocols for investigating potentially significant observations involving multiple independent research teams, peer review processes, and systematic comparison against established theoretical frameworks. When scientists like Loeb propose unconventional interpretations, these institutional mechanisms provide structured approaches for testing alternative hypotheses. The agency also considers broader implications of public communication about controversial topics. NASA serves multiple constituencies, including scientific communities, political oversight bodies, international partners, and general public audiences. Statements about potential extraterrestrial technology must balance scientific honesty with institutional responsibilities for maintaining appropriate public understanding of space exploration research and planetary defense activities. Statler's background in planetary defense adds another dimension to his institutional perspective on 3I@L. Through work with the Planetary Defense Coordination Office, he understands how public reactions to asteroid and comet discoveries can influence political support for detection and mitigation programs. Speculation about alien spacecraft risks distracting from real planetary defense needs, while potentially undermining public confidence in NASA's ability to distinguish genuine threats from natural phenomena. The scientists' measured responses also reflect awareness of scientific reputation and career considerations within institutional contexts. Unlike independent researchers like Loeb, NASA scientists must balance individual intellectual curiosity with organizational priorities and professional advancement within government bureaucratic structures. Taking public positions on controversial topics requires careful consideration of potential consequences for both personal career trajectory and institutional mission effectiveness. Nevertheless, Statler maintains openness to genuinely anomalous observations that might challenge conventional understanding. His institutional role requires evaluating evidence systematically, regardless of whether results support expected theoretical frameworks. If 3I Atlas displayed clear signatures of technological origin, NASA protocols would require appropriate investigation and communication of findings, even if such conclusions proved professionally or institutionally uncomfortable. The lead scientist's technical background also informs his confidence in natural explanations for 3I Atlas characteristics. Through missions like Lucy, which explores Trojan asteroids, and MMX, which will study the moons of Mars, Statler works regularly with objects displaying unusual properties that initially appeared mysterious. Experience teaches that seemingly anomalous observations often yield conventional explanations once sufficient data becomes available and appropriate theoretical frameworks are applied. Statler noted that 3I Atlas would not approach closer than about 170 million miles from Earth due to planetary orbital mechanics over the coming months. This trajectory analysis represents routine computational work for NASA scientists who track thousands of small bodies throughout the solar system. The calculations demonstrate normal gravitational dynamics rather than controlled maneuvering that might suggest artificial guidance systems. As autumn 2025 progressed and 3I Atlas moved closer to the Sun, Statler continued providing institutional perspective on emerging observational data. Each new measurement offered opportunities to test competing hypotheses about the object's nature while demonstrating NASA's systematic approach to scientific investigation. The process illustrates how established institutions evaluate extraordinary claims through methodical accumulation and analysis of evidence. The controversy surrounding 3I Atlas thus reveals essential tensions between individual scientific speculation and institutional scientific communication. While researchers like Loeb can advance unconventional hypotheses without immediate consequences for large organizational missions, institutional scientists must balance intellectual openness with responsibilities for maintaining public trust and professional credibility. These different constraints shape how various experts approach the same observational data and theoretical questions. Through careful words and measured assessments, Tom Statler exemplifies NASA's institutional approach to managing scientific controversies involving potentially extraordinary claims. His responses to 3IATL's speculation demonstrate how government science agencies navigate between premature dismissal of unconventional possibilities and premature endorsement of inadequately supported hypotheses. This institutional role remains crucial for maintaining both scientific integrity and public confidence in space exploration research as humanity continues searching for answers to fundamental questions about our place in the universe. Comets are supposed to follow predictable patterns. When frozen chunks of rock and ice approach the sun, they warm up, release gas, and develop characteristic tails pointing away from our star. Astronomers have observed thousands of these celestial wanderers over centuries, building detailed models of how they behave at different distances from the sun. 3I Atlas should follow these same patterns, yet its behavior challenges fundamental assumptions about cometary physics in ways that leave even skeptical scientists genuinely puzzled. The first troubling evidence emerged from pre-recovery observations made by NASA's Transiting Exoplanet Survey satellite, known as TESS. These measurements, taken between May 7th and June 3rd, 2025, revealed that 3 Atlas was already bright and active when it was approximately 6.4 astronomical units from the Sun. For context, most comets remain dormant at such distances, only beginning significant activity when they reach about 3 astronomical units from our star. This early activity suggests that 3 Atlas contains unusual volatile materials that sublimate at much lower temperatures than typical water ice. Spectroscopic analysis later confirmed the object possesses extraordinarily high concentrations of carbon dioxide compared to water vapor. The Very Large Telescope in Chile detected carbon dioxide emissions so intense that they overwhelmed typical cometary signatures, creating an 8-to-1 ratio favoring carbon dioxide over water in the object's coma. Such extreme ratios have never been observed in any comet from our solar system, even comets originating from the distant Oort cloud, where carbon dioxide should be more prevalent due to lower formation temperatures, typically display much more balanced compositions. The chemical signature of 3 IATLs suggests formation conditions unlike anything found in our local stellar environment over the past 4.5 billion years. NASA's James Webb Space Telescope provided additional disturbing details when it observed 3 IATLs using its N-ear spec instrument on August 6th. The space-based infrared observatory detected not only the unusual carbon dioxide dominance, but also trace amounts of carbon monoxide and carbonyl sulfide mixed with surprisingly small quantities of water, ice, and vapor. This composition pattern defies theoretical models for comet formation in any known stellar system. The brightness characteristics of 3 Iatelis present another fundamental puzzle that challenges astronomical understanding. Initial estimates, based on reflected sunlight, suggested the object measured between 10 and 20 kilometers in diameter, making it enormous compared to previous interstellar visitors. Oumuamua measured roughly 200 meters at its longest dimension, while Comet Borisov stretched less than 1 kilometer across. If 3 Iatelis truly reached 20 kilometers in diameter, it would represent a mass roughly 1 million times greater than its predecessors. However, subsequent observations by the Hubble Space Telescope constrained the nucleus diameter to between 320 meters and 5.6 kilometers, with the most likely size being less than 1 kilometer. This created a brightness paradox. The object reflected far more light than its actual size should allow, even accounting for its surrounding coma. The discrepancy suggests either unusual surface composition or geometric properties that violate standard assumptions about cometary reflectance. Adding to the mystery, ground-based polarimetric observations revealed that 3 I-Atlas exhibits unusually high degrees of negative polarization at small phase angles. This means a large percentage of light reflected from its coma has oscillations oriented along the Sun-Comet observer plane. Such polarization patterns typically occur only in trans-Neptunian objects with surfaces containing mixtures of icy and dark carbonaceous materials. No interstellar comet should display these characteristics. The Very Large Telescope made even more troubling discoveries when it detected atomic nickel vapor in the coma of 3 Ia-Elas. While nickel emissions have been observed in other comets, including the previous interstellar visitor Borisov, the concentrations found in 3 Ia-Elas appear without corresponding iron vapor signatures. Comets typically release nickel and iron in roughly equal proportions during outgassing processes, making the isolated nickel emissions genuinely anomalous. By August 21st, 2025, astronomers estimated that 3 Ia-TLS was releasing 4.6 grams of nickel per second and 17.6 grams of cyanide per second. These emission rates, while consistent with other comets at similar solar distances, occurred through chemical processes that remain poorly understood. Researchers proposed that nickel-containing organic compounds might decompose through space weathering effects, but no definitive mechanism has been confirmed. The trajectory characteristics of 3 Ia-Atlas add another layer of scientific concern. The object approaches the Sun on an orbital plane tilted only 5 degrees from the ecliptic, the plane containing most planetary orbits. Statistical analysis indicates that random interstellar objects should arrive with orbital inclinations distributed evenly across all possible angles. The probability of such precise alignment occurring by chance measures less than 0.2%. Furthermore, 3 Atlas will pass unusually close to multiple planets during its transit through our solar system. It approaches within 650,000 kilometers of Venus, 190,000 kilometers of Mars, and 360,000 kilometers of Jupiter. The combined probability of all 3 close encounters occurring for a randomly arriving interstellar object calculates to approximately 0.005%, a figure that troubles statisticians and orbital dynamicists. The timing of these planetary encounters creates additional puzzles for astronomers attempting to understand natural processes. 3 IATLs achieves its closest approach to the Sun, called perihelion, on October 29, 2025, when Earth lies on the opposite side of our star. This positioning makes detailed observations extremely difficult precisely when the object should display maximum activity and provide the most revealing data about its physical composition. Observations from multiple telescopes revealed that 3 Ia-Atlas lacks the extended dust tail characteristic of active comets. Despite releasing substantial quantities of gas and microscopic particles, the object fails to develop the streaming tail that solar radiation pressure typically creates. This absence contradicts basic physics of how solar wind and radiation interact with cometary debris, suggesting either unusual particle properties or geometric effects not predicted by current models. The Gemini South telescope in Chile captured images showing a developing tail during late August observations, but this feature appeared much shorter and fainter than expected based on the object's gas production rates. The mismatch between gaseous emissions and dust tail development indicates fundamental differences in how 3 Atlas responds to solar heating compared to familiar comets from our own stellar system. Spectroscopic analysis has failed to detect several molecular signatures that should be present in an active comet at 3 Atlas solar distance. Ground-based telescopes found no evidence of diatomic carbon, a molecule that typically appears as comets approach within 3 astronomical units of the Sun. The absence of this fundamental cometary tracer compounds questions about whether the object truly represents a conventional comet or something more unusual. Temperature measurements of 3I Atlas suggest surface heating patterns inconsistent with simple solar illumination of rotating icy bodies. Thermal infrared observations indicate that different regions of the object warm and cool at rates that do not match theoretical predictions for comets with typical compositions and structures. These thermal anomalies could result from unusual internal heat sources or exotic surface materials not found in solar system objects. The velocity profile of 3 Atlas as it approaches the inner solar system displays subtle variations that puzzle orbital mechanics specialists. While the object generally follows the hyperbolic trajectory expected for an interstellar visitor, minor deviations from pure gravitational motion suggest either non-gravitational forces from asymmetric outgassing or systematic measurement errors in tracking observations. Neither explanation fits comfortably with other observational data. Attempts to determine the rotation period of 3 Atlas through brightness variations have produced inconsistent results. Different observing teams report rotation periods ranging from several hours to multiple days, with some suggesting the object may not rotate regularly at all. Such rotational ambiguity indicates either complex geometrical properties or unusual mass distribution that defies simple interpretation based on conventional cometary models. The chemical isotope ratios, measured in 3 IATL's gas emissions, suggest formation in environments with different nuclear processes than those that created our solar system. Preliminary analysis indicates deuterium concentrations and carbon isotope signatures consistent with formation around stars with different metallicity and age characteristics. These chemical fingerprints support genuine interstellar origin while raising questions about the diversity of planetary formation processes throughout the galaxy. Radio telescope observations have detected no artificial signals or structured emissions from 3 IATLAs, despite extensive monitoring by facilities equipped for such measurements. The Search for Extraterrestrial Intelligence Institute conducted systematic scans across multiple frequency bands without finding evidence of technological signatures. This absence of artificial emissions provides some evidence against technological origin hypotheses, while leaving other anomalous characteristics unexplained. Ground-based photometric monitoring reveals that 3 Atlas brightens and dims in patterns that do not correspond to typical cometary behavior, rather than steady increases in brightness as the object approaches the sun. Measurements show irregular fluctuations that suggest either complex surface properties or internal activity sources unrelated to simple solar heating. These brightness variations challenge basic assumptions about how interstellar objects should respond to changing solar illumination. The plasma environment around 3I ATLAS, detectable through radio emissions and magnetic field measurements, displays properties inconsistent with normal cometary plasma interactions. Solar wind particle detectors indicate unusual electromagnetic signatures as the solar wind encounters gas and dust streaming from the object. These plasma anomalies could result from exotic chemical compositions or magnetic field structures not previously observed in cometary environments. Recent observations by the newly commissioned Vera Rubin Observatory revealed that 3I Atlas displayed measurable brightness variations during June and early July 2025, before its official discovery. These pre-recovery measurements show the object was significantly more active earlier in its approach than theoretical models predicted. The early activity onset suggests volatile materials with sublimation temperatures far below those of water ice, consistent with the later discovery of extreme carbon dioxide dominance. As 3ITLS continues its approach toward perihelion, each new observation adds to the growing catalog of characteristics that challenge conventional understanding of interstellar comets. While none of these anomalies individually proves artificial origin or exotic composition, their collective presence creates a scientific puzzle that troubles astronomers committed to explaining natural phenomena through established physical principles. The object serves as a humbling reminder that the universe contains processes and materials that exceed current theoretical frameworks, regardless of whether those mysteries ultimately yield to natural or more extraordinary explanations. In the quiet corridors of the International Astronomical Union headquarters, decisions about cosmic nomenclature rarely generate headlines. The organization's working group on small bodies nomenclature operates with methodical precision, following protocols developed over decades to bring order to the vast catalog of objects that populate our solar system. Yet when 3ITLS appeared in observatory data on July 1st, 2025, its classification challenged these established systems in ways that revealed the fundamental assumptions underlying how humans organize the cosmos. The modern astronomical naming system evolved from centuries of increasingly systematic approaches to celestial taxonomy. Early astronomers simply named comets after the years when they appeared, creating designations like the Great Comet of 1680. As observations became more frequent and detailed, conventions arose using discoverer names, leading to familiar designations like Halley's Comet or Comet Hale-Bopp. By the 20th century, however, technological improvements and dedicated search programs generated far too many discoveries for personal naming systems to remain practical. The International Astronomical Union responded by developing coded designation schemes that could accommodate unlimited discoveries while providing systematic information about each object's characteristics. Under current protocols, comets receive provisional designations consisting of the discovery year, a letter indicating the half-month of discovery, and a number showing the sequence within that period. Thus, the fourth comet discovered in the second half of February 2006 becomes designated 2006 D4. More importantly, prefix letters indicate fundamental categorizations about each object's nature and orbital behavior. The letter P designates periodic comets with orbital periods less than 200 years or confirmed observations at multiple perihelion passages. The letter C indicates non-periodic comets, meaning objects with longer periods or single observed passages. These distinctions reflect deep assumptions about how objects interact gravitationally with our Sun and what such interactions reveal about their origins and compositions. Additional prefixes address special circumstances that challenge simple classification schemes. The letter X marks comets with unreliable orbital calculations, typically historical objects with incomplete observational records. The letter D indicates periodic comets that have disappeared, broken up, or been lost to continued observation. The letter A designates objects initially misclassified as comets but later recognized as minor planets or asteroids. These categories acknowledge the fundamental difficulty of distinguishing between object types based on limited observational data. When Oumuamua passed through our solar system in 2017, it exposed critical gaps in existing classification systems. The object was first designated as Comet C 2017 U1 based on its hyperbolic trajectory and apparent origin from interstellar space. However, it showed no evidence of cometary activity such as coma formation or tail development, leading to reclassification as Asteroid A 2017 U1 when orbital analysis confirmed its interstellar origin. The International Astronomical Union faced a classificatory crisis requiring entirely new nomenclature categories. The organization responded by creating the I prefix specifically for interstellar objects, allowing the reclassification of Oumuamua as 1I 2017 U1. This designation acknowledges the object's interstellar origin while remaining agnostic about whether it represents an asteroid, comet, or something entirely different. The precedent established a framework that would prove essential when subsequent interstellar visitors required classification under similarly ambiguous circumstances. 2I Borisov, discovered in 2019, fit more comfortably within existing conceptual frameworks. The object displayed clear cometary characteristics, including coma formation and tail development, making its classification relatively straightforward despite its interstellar origin. Spectroscopic analysis revealed chemical compositions broadly consistent with comets from our solar system, supporting conventional theoretical understanding of how such objects form and evolve in different stellar environments. 3I et al.'s presented far greater classificatory challenges when it arrived in 2025. Initial observations suggested clear cometary activity with coma formation and brightness variations consistent with solar heating of volatile materials. These characteristics supported straightforward classification as an interstellar comet, following the precedent established by Borisov. However, detailed analysis revealed anomalous properties that strained the boundaries between established categories. The extreme carbon dioxide to water ratio detected in 3I Atlas contradicts fundamental assumptions about cometary composition that underlie the comet classification itself. Comets are defined partly by their behavior as they approach the sun, developing characteristic tails through sublimation of water ice and other volatile materials. Objects with radically different compositions might behave in ways that challenge whether they belong in the comet category at all, regardless of their general resemblance to cometary phenomena. Similarly, the unusual brightness characteristics of 3I Tellus create taxonomic puzzles about size and composition relationships. The classification system assumes that brightness correlates predictably with object size and surface reflectance properties. When these relationships break down, as they appear to with 3I Tellus, the fundamental basis for distinguishing between comets and asteroids becomes questionable. An object might display cometary activity while possessing asteroid-like structural properties, or vice versa. The International Astronomical Union operates through consensus-building processes that require broad agreement among professional astronomers before adopting new classificatory schemes. These procedures work well for incremental refinements to existing systems, but struggle with objects that fundamentally challenge underlying assumptions. 3 Atlas represents exactly such a challenge, displaying characteristics that span multiple traditional categories while fitting none of them perfectly. Institutional momentum within the astronomical community favors conservative approaches to classification changes. Researchers invest decades building expertise around specific object types, developing specialized instruments and theoretical models based on established categories. When anomalous objects suggest that these categories might be incomplete or incorrect, professional communities face difficult choices between maintaining consistency with past work and acknowledging new complexities that require revised frameworks. The Working Group on Small Bodies Nomenclature must balance multiple competing interests when addressing classificatory challenges. Scientific accuracy demands categories that reflect genuine physical distinctions between different object types. Historical consistency requires maintaining compatibility with existing databases and research programs. International coordination necessitates systems that work across different languages, institutions, and technological capabilities. Public communication benefits from categories that remain comprehensible to non-specialist audiences interested in space exploration. The 3I Atlas controversy highlights fundamental philosophical questions about how scientific classification systems should respond to boundary cases that don't fit established patterns. Conservative approaches emphasize maintaining existing categories until overwhelming evidence demonstrates their inadequacy. Progressive approaches advocate for more flexible systems that can accommodate greater diversity in object characteristics without forcing artificial distinctions based on incomplete understanding. Professional astronomers working with 3I Atlas face practical decisions about how to describe the object in research papers, grant applications, and public communications. Different classificatory choices carry implications for which theoretical frameworks apply, which comparison objects are relevant, and which research communities should be engaged in ongoing studies. These seemingly technical decisions about nomenclature directly influence how scientific knowledge develops and spreads. The debate over 3 Atlas classification also reflects broader questions about how science handles uncertainty and anomalous observations. Traditional approaches treat unusual characteristics as measurement errors or theoretical gaps that will eventually be resolved through better data or refined models. Alternative approaches suggest that some anomalous objects might represent genuinely new phenomena that require expanded theoretical frameworks rather than incremental modifications to existing understanding. Educational institutions teaching introductory astronomy courses struggle with how to present object classification systems when boundary cases challenge simple distinctions. Students learning to distinguish between comets and asteroids need clear criteria they can apply reliably, but real objects sometimes display characteristics that span multiple categories. 3I Atlas serves as a pedagogical challenge that exposes the limitations of simplified taxonomic schemes while illustrating the dynamic nature of scientific knowledge. International cooperation in astronomy depends heavily on shared classificatory standards that enable researchers from different countries and institutions to communicate effectively about their observations. When objects like 3I Atlas challenge these standards, the international astronomical community must develop new consensus approaches through formal and informal coordination mechanisms. The process reveals both the strengths and limitations of current international scientific governance structures. The precedent set by 3 Atlas classification decisions will influence how future anomalous objects are categorized and studied. If the astronomical community adopts more flexible approaches that acknowledge classificatory uncertainty, subsequent discoveries might be described with greater precision and nuance. If more conservative approaches prevail, future objects might be forced into inappropriate categories that obscure their genuine characteristics and limit productive research directions. As observations of 3I Atlas continue throughout its solar system passage, new data may resolve some classificatory ambiguities while revealing others. The object serves as a natural experiment in how scientific communities adapt their organizational frameworks when confronted with phenomena that exceed existing theoretical boundaries. Whether those adaptations prove adequate for understanding 3I Atlas and similar objects will determine how effectively astronomy evolves to encompass the full diversity of cosmic phenomena awaiting discovery. The process by which discovery becomes classification thus reveals the deeply human dimensions of scientific knowledge. Even the most objective observational data must be interpreted through conceptual frameworks developed by particular communities operating under specific historical and institutional constraints. 3I Atlas challenges those frameworks in ways that illuminate both their utility and their limitations, ultimately demonstrating that the cosmos contains more diversity than any human organizational system can fully capture. What does it mean to truly see an object millions of miles away? For most of human history, comets appeared as fuzzy smudges moving across the night sky, their true nature hidden behind the limitations of human vision. Today, 3 Atlas passes through our solar system, observed by an unprecedented array of sophisticated instruments, each revealing different aspects of its composition and behavior. Yet paradoxically, the more we can see, the more mysterious this visitor becomes. The Hubble Space Telescope, orbiting above Earth's atmospheric interference, captured the first detailed images of 3I Atlas on July 21st, 2025. Free from the blurring effects of air currents and weather, Hubble's observations revealed intricate structure within the object's coma that ground-based telescopes could barely detect. The space-based observatory constrained the nucleus diameter to between 320 meters and 5.6 kilometers, providing crucial data for understanding the object's mass and composition. Hubble's high-resolution imagery also revealed asymmetric brightness patterns within 3A Atlas's coma that defied simple explanations. Rather than displaying the symmetric glow expected from uniform solar heating, the object showed concentrated brightness regions that suggested either complex internal structure or unusual surface composition. These patterns became fodder for speculation about whether natural processes could account for such organized appearances. The James Webb Space Telescope brought unprecedented infrared capabilities to bear on 3I Atlas when it observed the object using its N-IR spec instrument on August 6, 2025, operating in wavelength ranges invisible to human eyes. Webb detected molecular signatures that revealed the object's extreme carbon dioxide dominance and unusual chemical composition. The space-based infrared observatory provided data impossible to obtain from ground-based telescopes affected by atmospheric absorption. Webb's spectroscopic analysis revealed not just the presence of different molecules, but their relative concentrations and physical states within 3I Atlas's coma. The 8-to-1 ratio of carbon dioxide to water vapor that emerged from these observations challenged every existing model of cometary composition. No object in our solar system displays such extreme ratios, making 3 Ayatollahs a unique laboratory for studying exotic volatile behavior. Ground-based observatories contributed essential complementary observations that space telescopes couldn't provide. The Very Large Telescope in Chile's Atacama Desert used its massive collecting area to detect faint spectral signatures of nickel and cyanide in 3 Ayatollahs' coma. These metallic emissions, while present in other comets, appeared in unusual concentrations and patterns that added to the object's growing catalog of anomalous characteristics. The Gemini South Telescope captured images showing 3 Atlas developing what appeared to be a conventional cometary tail during late August 2025. However, the tail's faintness relative to the object's gas production rates suggested either unusual particle properties or geometric effects not predicted by standard cometary models. The mismatch between different observational signatures illustrated how multiple instruments could observe the same object, yet reveal seemingly contradictory information. Radio telescopes provided another crucial perspective by monitoring electromagnetic emissions from 3 ATLAS across frequencies ranging from megahertz to gigahertz. The Search for Extraterrestrial Intelligence Institute conducted systematic scans without detecting artificial signals, providing evidence against technological origin hypotheses while leaving other anomalous characteristics unexplained. The absence of structured radio emissions represented one data point supporting natural origin, even as other observations raised questions. Polarimetric observations by multiple ground-based telescopes revealed that 3 Atlas exhibits unusual light scattering properties compared to typical comets. The object's high degree of negative polarization at small phase angles suggests surface materials with different optical characteristics than those found in solar system objects. These measurements require specialized instruments and careful calibration, making them among the most technically demanding observations conducted. The newly commissioned Vera Rubin Observatory serendipitously captured 3 IATLs during science validation observations between June 21st and July 3rd, 2025. The Wide Field Survey Telescope's sensitive detectors showed that the object was already active when still far from the Sun, consistent with later discoveries about its unusual volatile composition. Rubin's automated detection systems illustrated how modern sky surveys can identify interesting objects even before human astronomers recognize their significance. NASA's Transiting Exoplanet Survey satellite had unknowingly observed 3 Atlas even earlier, between May 7th and June 3rd, 2025, before its official discovery. These pre-recovery observations showed consistent brightness, indicating early cometary activity at distances where most comets remain dormant. The space-based photometry provided crucial baseline data for understanding how 3 Atlas evolved as it approached the inner solar system. Different instruments revealed 3 Atlas at different wavelengths, creating a composite portrait that no single observatory could provide alone. Visible light observations showed its overall brightness and coma structure. Infrared measurements detected molecular signatures and thermal emissions. Ultraviolet observations revealed ionized gas in the object's vicinity. Radio monitoring searched for artificial signals. Together, these multi-wavelength studies created the most comprehensive observational dataset ever assembled for an interstellar visitor. Yet this wealth of data also exposed the limitations of current observational capabilities. No existing instrument could simultaneously measure all the characteristics needed to definitively determine 3-Adiolaz's nature and origin. Spectroscopic observations required long exposures that lost temporal resolution. High-resolution imaging sacrificed spectral information. Ground-based telescopes provided continuous monitoring but suffered atmospheric interference. Space-based instruments offered superior sensitivity but limited observing time. The coordination required to organize observations across multiple facilities illustrated both the strengths and challenges of modern astronomical research. International scheduling committees had to balance competing demands from hundreds of research projects while ensuring optimal coverage of 3 Atlas during its brief passage. Some crucial observations were delayed or missed entirely due to weather, equipment failures, or scheduling conflicts that revealed the fragility of our observational capabilities. Amateur astronomers contributed valuable observations using smaller telescopes and less sophisticated equipment than professional observatories. Their continuous monitoring provided data during periods when major facilities were occupied with other projects. Some amateur observations detected brightness variations or structural changes that professional astronomers might have missed due to their focus on specific research questions. The collaboration between professional and amateur observers demonstrated the distributed nature of modern astronomical discovery. Each instrument brought its own systematic errors, calibration uncertainties, and observational biases that could influence interpretations of 3 ITLAS data. Subtle differences in how different telescopes measure brightness, color, or spectral features could create apparent discrepancies that might be mistaken for genuine physical phenomena. Understanding these instrumental effects required careful cross-calibration and statistical analysis that added complexity to seemingly straightforward observations. The data analysis pipeline for 3 IATL's observations involved dozens of software packages, theoretical models, and statistical techniques developed by different research groups over many years. Each processing step introduced potential systematic errors or theoretical assumptions that could influence final results. Trace contamination from terrestrial atmospheric emissions, instrumental artifacts, or cosmic ray impacts could create false signatures that might be mistaken for genuine physical phenomena. Advanced imaging techniques allowed astronomers to separate light from 3 IATLAS's nucleus from emissions originating in its coma, providing better estimates of the object's size and surface properties. However, these techniques relied on theoretical models of how light scatters from dust and gas mixtures that might not apply to 3 IATLAS's unusual composition. The separation between different emission components remains somewhat artificial, imposed by analysis methods rather than reflecting clear physical boundaries. Temporal monitoring by multiple instruments revealed that 3 Atlas's properties changed as it approached the Sun, but the rate and nature of these changes didn't match predictions from standard cometary models. Some characteristics brightened faster than expected, while others evolved more slowly. These temporal patterns provided crucial clues about internal structure and composition, but interpreting them required theoretical frameworks that might not apply to such an anomalous object. The combination of space-based and ground-based observations created unprecedented three-dimensional views of three atlases coma and tail structure. Different viewing angles and wavelengths revealed asymmetries and substructures that suggested complex internal processes. However, reconstructing the true three-dimensional geometry from two-dimensional projections required assumptions about symmetry and orientation that might not hold for such an unusual object. Future observations of 3IS will depend on instruments currently under development or planned for construction. The extremely large telescope will provide higher resolution and greater sensitivity than any existing facility. Next generation space telescopes will offer improved spectroscopic capabilities and longer observing opportunities. These future observations might resolve current uncertainties or reveal new anomalies that further complicate our understanding. The 3I Atlas observational campaign thus represents both the pinnacle of current astronomical capabilities and a demonstration of their limitations. Our most sophisticated instruments reveal an object that challenges fundamental assumptions about cometary behavior while leaving many questions unanswered. The case illustrates how even comprehensive multi-wavelength observations can create more mysteries than they solve when confronted with phenomena that exceed existing theoretical frameworks. As 3IATLs continues its journey toward the outer solar system, the window for detailed observations gradually closes. The object becomes fainter and more difficult to study, limiting future opportunities to resolve the puzzles it presents. The observational campaign serves as a reminder that astronomical discovery depends not just on sophisticated instruments, but on the brief moments when interesting objects pass close enough to Earth for detailed study. Across the frozen depths of interstellar space, between star systems separated by trillions of miles, chemical processes unfold that dwarf anything occurring within our familiar solar neighborhood. When 3I Atlas formed around a distant star billions of years ago, the composition of gas and dust in that alien environment created frozen materials unlike anything found in objects native to our own stellar system. The extreme carbon dioxide to water ratio discovered in its coma tells a story written in molecular signatures about conditions that existed when the universe was young and different. The detection of overwhelming carbon dioxide emissions from 3 Eddysthes challenged every theoretical model astronomers use to understand cometary formation and evolution. Most comets in our solar system contain roughly equal amounts of carbon dioxide and water ice, with water typically dominating at the 8-to-1 ratio observed in 3 Eddysthes reverses this expectation so dramatically that it suggests formation under completely different physical and chemical conditions than those that shaped objects in our cosmic neighborhood. Understanding how such extreme ratios could develop requires examining the stellar nucleosynthesis processes that create heavy elements in the hearts of dying stars. Different types of stars produce different ratios of carbon, oxygen, and other elements depending on their mass, age, and evolutionary stage. When these stars explode as supernovae or shed their outer layers as planetary nebulae, they distribute their nuclear products throughout nearby space, seeding the raw materials from which new planetary systems eventually form. The chemical fingerprints detected in 3I Atlas suggest formation around a star with significantly different metallicity than our Sun. Older stars formed when the universe contained fewer heavy elements, creating different ratios of carbon to oxygen in their surrounding protoplanetary disks. Comets forming in such environments would naturally incorporate the available materials, resulting in compositions that reflect the nuclear history of their parent star rather than the solar conditions familiar to us. Spectroscopic analysis by the James Webb Space Telescope revealed not just carbon dioxide, but also trace amounts of carbon monoxide and carbonyl sulfide mixed with surprisingly small quantities of water vapor and ice. This molecular cocktail suggests that 3I Atlas formed in a region where carbon bearing compounds dominated over oxygen bearing species, possibly around a carbon star or in the aftermath of a carbon rich supernova explosion. The temperature and pressure conditions during 3 Atlas formation also influenced which molecules could condense into solid form and become incorporated into the growing comet nucleus. In colder regions of protoplanetary disks, carbon dioxide freezes at higher temperatures than water, allowing it to condense first and potentially dominate the final composition. If 3 Atlas formed in an unusually cold region of its parent system, this could explain the extreme carbon dioxide concentrations observed today. Chemical models of interstellar ice formation suggest that 3I Atlas might preserve materials that form directly in the interstellar medium rather than in a planetary disk around a specific star. Interstellar dust grains accumulate ice mantles through direct deposition from gas phase molecules over millions of years. These mantles can have very different compositions from ices formed in protoplanetary environments, potentially explaining some of 3I Atlas's anomalous characteristics. The organic chemistry occurring on interstellar dust grains involves complex reactions driven by cosmic radiation and ultraviolet light from nearby stars. These processes can create exotic organic compounds not found in solar system objects, including carbon-rich polymers and unusual molecular structures. Some of these interstellar organic materials might have been preserved within 3I Atlas, contributing to its unusual spectroscopic signatures. Isotope ratio measurements from 3I Atlas gas emissions provide additional clues about its formation environment. Different stellar environments produce different ratios of isotopes, like carbon 12 versus carbon 13 or oxygen 16 versus oxygen 18. Preliminary analysis suggests that 3I Atlas contains isotope ratios consistent with formation around older, metal-poor stars rather than younger systems like our own. The preservation of such ancient chemical signatures requires that 3A ATLs remained in cold, stable conditions for billions of years after its initial formation. Objects that experience significant heating or chemical processing would lose their original compositions through sublimation, chemical reactions, or phase transitions. The fact that 3A ATLs still retains its extreme carbon dioxide dominance suggests it has spent most of its existence in the frigid conditions of deep interstellar space. Galactic dynamics models indicate that objects can be ejected from their birth systems through gravitational interactions with giant planets, stellar companions, or close encounters with other stars. Once ejected, these interstellar wanderers travel through the galaxy for millions or billions of years, preserving chemical information from their original formation environments. 3 Atlas represents a time capsule carrying molecular memories from an era when stellar conditions differed significantly from today. The spatial distribution of chemical elements throughout the galaxy has evolved over cosmic time as successive generations of stars have processed primordial hydrogen and helium into heavier elements. Stars forming in different regions and epochs create planetary systems with different chemical compositions, leading to diversity in the types of comets and asteroids that form. 3I Atlas might sample this galactic chemical diversity. Laboratory studies of exotic ices under conditions simulating interstellar environments reveal complex phase behaviors and chemical reactions not observed in terrestrial settings. When carbon dioxide and water ices mix in different ratios and temperature histories, they can create layered structures, crystalline phases, and amorphous materials with different physical properties. These laboratory results help interpret the unusual behavior observed in 3IATLs. The sublimation behavior of carbon dioxide versus water ice differs significantly, with carbon dioxide transitioning directly from solid to gas at much lower temperatures than water. This means 3IATLs began outgassing carbon dioxide when it was still far from the sun, creating the early activity observed by NASA's TESS satellite. As it approaches closer to the sun, different volatile components activate at different distances, creating evolving chemical signatures. Theoretical models of how exotic ice mixtures respond to solar heating predict different brightness patterns, tail development, and coma structures than those observed in typical comets. The unusual appearance of 3 Atlas might result from its extreme chemical composition rather than any non-natural origin. However, matching theoretical predictions with observational data requires understanding chemical processes that have never been studied in detail. The discovery that 3A contains abundant nickel emissions without corresponding iron signatures suggests additional chemical complexities not captured in standard cometary models. Nickel-bearing organic compounds might form under specific interstellar conditions involving cosmic ray processing of metal-rich dust grains. The decomposition of these compounds as 3A heats up could explain the observed metallic emissions. Chemical evolution in interstellar environments operates on timescales of millions to billions of years, allowing slow reactions and phase transitions that don't occur in laboratory settings or planetary system environments. 3I Atlas might preserve the products of these ultra-long timescale chemical processes, making it a unique laboratory for studying chemical evolution under conditions that no longer exist in accessible locations. The implications of 3 Atelis's chemical composition extend beyond understanding the single object to broader questions about chemical diversity in planetary formation processes throughout the galaxy. If extreme compositions like this exist, they suggest that the range of possible planetary system architectures and chemical environments exceeds current theoretical frameworks significantly. Future spectroscopic observations as 3I Atlas approaches perihelion will reveal how its chemical emissions evolve under increasing solar heating. Different volatile components should activate in predictable sequences, providing tests of theoretical models about exotic ice behavior. If the observed patterns match predictions for extreme chemical compositions, it would support natural origin interpretations. However, if 3I Atlas continues displaying chemical signatures that don't match any theoretical framework for natural comet formation and evolution, it would strengthen arguments for more exotic origins. The chemical evidence provides one of the most objective tests available for distinguishing between natural and artificial interpretations of its anomalous characteristics. The carbon dioxide snow preserved within 3I Atlas thus serves as both a messenger from ancient stellar environments and a challenge to current understanding of chemical processes in planetary formation. Whether these chemical mysteries ultimately yield to expanded natural theories or require consideration of more extraordinary possibilities will depend on how well future observations match theoretical predictions about exotic cometary chemistry. The molecules themselves remain silent witnesses to conditions that existed when the universe was younger, and the chemistry of star formation followed different pathways than those familiar from our local stellar neighborhood. Could probability theory prove extraterrestrial visitation? When Avi Loeb calculated the statistical likelihood of 3 Atlas' precise trajectory through our solar system, he uncovered numbers so small they challenged conventional understanding of cosmic coincidence. The object's orbital plane alignment within 5 degrees of Earth's ecliptic occurs with probability less than 0.2% for random interstellar visitors. Its close approaches to Venus, Mars, and Jupiter combined represent odds of approximately 0.005%. These mathematical realities forced even skeptical astronomers to acknowledge that 3 Atlas follows an unusually precise geometric path through our planetary neighborhood. Statistical analysis of interstellar object trajectories relies on fundamental assumptions about how such objects should behave if ejected randomly from distant stellar systems. Computer simulations model billions of possible ejection scenarios, tracking how objects would arrive at our solar system after millions of years in interstellar space. The vast majority of these simulated objects arrive with orbital inclinations distributed evenly across all possible angles, not concentrated near the ecliptic plane where 3A Tls travels. In the controlled environment of the Green Bank Observatory in West Virginia, radio telescopes sweep across 3 Iteles with methodical precision, listening for any structured signal that might indicate artificial origin. Month after month, the cosmic visitor maintains perfect radio silence. No modulated transmissions emerge from its coma, no encrypted data streams leak from its nucleus. The absence of artificial signals provides one of the strongest arguments against technological origin. Yet paradoxically, this very silence troubles some researchers who wonder whether truly advanced technology might operate beyond current detection capabilities. The search for extraterrestrial intelligence protocols developed over decades assumed that technological objects would emit detectable electromagnetic radiation, either intentionally as communication attempts or inadvertently as operational byproducts. 3I Atlas emits only natural thermal radiation and scattered sunlight, behaving exactly as a conventional comet should in the radio spectrum. This electromagnetic quietude supports NASA's institutional position while leaving other anomalous characteristics unexplained. NASA's measured response to 3 Atlas speculation reflects hard-learned lessons from previous encounters with anomalous space objects. The agency's experience with Oumuamua taught institutional leaders about how quickly preliminary observations can escalate into public controversy when coupled with extraordinary claims. Internal protocols now emphasize conservative communication strategies that acknowledge unusual characteristics while maintaining appropriate scientific skepticism about exotic interpretations. The institutional memory embedded in NASA's approach extends beyond individual scientific assessments to encompass broader organizational considerations about public trust, political support, and international cooperation. When Tom Statler emphasizes that 3I Atlas behaves like other comets, he speaks not just as an individual scientist, but as a representative of institutional expertise built through decades of space exploration missions and scientific discoveries. Astronomers observing 3I Atlas during a lunar eclipse in September 2025 captured images showing the object glowing with an unusual green coloration. Unlike typical cometary appearances, spectroscopic analysis revealed this green light originates from diatomic carbon emissions, molecules that form when carbon bearing compounds break down under solar radiation. While diatomic carbon appears in other comets, the intensity and persistence of emissions from 3I Atlas exceed normal patterns significantly. The chemistry behind 3I Atlas's green glow involves complex molecular processes occurring within its coma as carbon dioxide and other exotic ices sublimate under solar heating. Different molecular fragments absorb and emit light at characteristic wavelengths, creating the distinctive green appearance that made the object visible to naked eye observers during favorable viewing conditions. These emissions provide additional evidence for the object's unusual chemical composition while demonstrating natural processes that could explain its anomalous characteristics. Behind NASA's carefully measured public statements about 3I Atlas lie institutional limitations that constrain how government scientists can discuss controversial topics involving potential extraterrestrial phenomena. The agency operates under congressional oversight, international treaty obligations, and administrative policies that prioritize certain types of research questions while limiting others. When Tom Statler states that evidence overwhelmingly supports natural origin, he communicates both scientific assessment and institutional position shaped by broader organizational constraints. The space between definitive knowledge and complete ignorance creates challenging territory for institutional science communication. NASA scientists must balance honest acknowledgement of observational uncertainties against premature speculation that could undermine public confidence or create unrealistic expectations. 3 Atlas exemplifies this communicative challenge by presenting genuine scientific mysteries within a context of extraordinary claims that exceed institutional comfort zones. Future observations of 3I Atlas, as it continues toward perihelion, will provide crucial tests of competing hypotheses about its nature and origin. NASA's planned monitoring efforts, using multiple space-based and ground-based instruments, will generate the most comprehensive dataset ever assembled for an interstellar visitor. Whether this additional evidence resolves current controversies or deepens existing mysteries will determine how the scientific community ultimately interprets this remarkable cosmic encounter. The institutional response to 3I Atlas thus reflects broader questions about how government science agencies should handle discoveries that challenge conventional understanding while generating public speculation about extraordinary possibilities. The careful balance between scientific openness and institutional responsibility continues evolving as NASA navigates the space between known physics and unknown phenomena that exceed current theoretical frameworks. As 3 Atlas approaches its closest point to the Sun and begins its journey back toward interstellar space, It leaves behind a changed scientific community that has grappled with questions extending far beyond this single object. The institutional, observational, and theoretical challenges it presented will influence how future anomalous discoveries are investigated, interpreted, and communicated to both scientific colleagues and the broader public interested in humanity's place in the cosmos.